Hey everybody, welcome to Reactions of Organic Chemistry, part the third. This sequel being subtitled Carboxylic Acids and Derivatives. Not quite as exciting a sequel name as Too Fast, Too Furious, or now Furious 7, but here we are nonetheless talking about something that is, I think we'll all agree, as exciting as the Fast and the Furious. Reactions of Organic Chemistry. You guys give me a thumbs up down there in chat if you can see and or hear and or possibly see and hear me. Yay! Welcome everyone. If you are, Zachary's got two left hands. That's amazing. If you are coming back from Eli's session, welcome. We are going to continue that rousing rendition of content with some more super important content. If you are just joining us for Organic Chemistry, then welcome to you as well. You are certainly all welcome to benefit from this session. You know, a really important thing happened last weekend. I don't know if you guys heard about this. It was all over the news. It was plastered in billboards across Times Square. They finally had the first MCATs ever. Oh my goodness, we've been waiting for like a year for this moment. You know what my friends who told me about the new MCAT said about the amount of organic chemistry on that test? Less! Very little. Yeah, not a lot of explicit organic chemistry. Because what the AMC has done with this new test is something that they have been pushing towards for the last several years. They finally flipped the switch from teaching or testing organic chemistry directly in a biochem context to testing biochem directly, but motivating it by organic chemistry. Because, for example, gang, if we talk about, that kind of bond that holds together amino acids, what is that kind of a bond, by the way, that holds together amino acids in a protein? Peptide bond. Yeah, what functional group does that represent, a peptide bond? We got an amino group binding to a carbonyl group. When I stick an amino group and a carbonyl group together, Lindsay's our lucky winner. I see Gabriella got it first as well. An amide, yeah. So while the MCAT may officially, formally, explicitly test biochemistry, you guys got to recognize that's a bit like saying you're going to be tested on calculus. Well, you need to know algebra to do calculus. You're going to be tested on biochemistry on the MCAT. You're going to need to know organic chemistry to be successful in that biochemistry. And I realized that was a bad example right away. Let me be very clear. You are not tested on calculus on the MCAT, but in the same way that if you've taken a calculus class, it's based on algebra, your biochemistry is going to be based on organic chemistry. So we definitely still do need to know the nomenclature, the properties of carboxylic acids, the different types of reactions that have carboxylic acids, and the various derivatives of carboxylic acids. These are all highly testable features of the MCAT, even if they are not necessarily going to show up in a more explicit format. That's what we're covering in this class session. You see some very common reactions here. That compound certainly looks quite familiar. Oh, that's aspirin. Yeah, so I guess there's a biochemistry aspect of chemistry, organic chemistry right here, right now. This is a synthetic pathway to make the compound aspirin. You guys are certainly familiar with that particular compound. So what we're going to see are some of the features that can be illustrated. And while we're not going to study this mechanism directly, this really illustrates a lot of our learning goals today. For example, we're trying to learn about the nomenclature and properties of carboxylic acids. Here we see carboxylic acids in a common biologically active molecule. So you see some different names of acids and these kinds of things. Let's take a look at nomenclature of carboxylic acids. The most obvious question, you guys know it's coming, I have to ask it. What suffix do we give to carboxylic acids? Oic acid. Yeah, exactly. So that's a big thing to recognize. And of course, on test day, you are never going to name that molecule. You're never going to do it. You're just not going to sit down and write down the name of that molecule like you would in organic chemistry class. You're going to pick the right name of that molecule out of 4 possibilities, And the suffix is a great place to start. If you see an answer choice that ends in own or all or something like that, you'll know right away that you are looking at the wrong name. Lauren, they didn't do that on the April administration of the MCAT. Do they still do it on the new MCAT? It is still fair game for the new MCAT. And I would expect that the May administration of the test looks very different from the April administration, since that's always been the case with the MCAT. So, again, while it didn't feature predominantly on the test that took place last weekend, it very well could take place on the test you're going to take in the future. And Eli's got a great point. Even if it's not like A, B, C, D, name these molecules, we still do need to recognize their names because they're going to show up in passages and these kinds of things. So, oic acid would be our suffix here. The root is consisting of 6 carbons hexanoic acid. And you guys all know we're going to treat that methyl group by designating the number of it and tacking it onto the name as well. 4-methyl hexanoic acid. Another thing that I did not want to click through quite as quickly here. Here we have a compound that is not 3-chlorobutanoic acid. Why would it not be appropriate to name this compound 3-chlorobutanoic acid? Yeah, we've deprotonated it. We're no longer looking at an acid at all. In fact, gang, when we deprotonated acid, what do we end up with? Yeah, we get a base. We get a base. Or, technically, Delisa points out, we have an anion, a basic anion, bound, in this case, to a salt, or to a cation giving us a salt. But we get the conjugate base, so we're going to appropriately name this molecule. I see some people punching in there. Instead of having oic acid, we're going to change the name to butanoate. Notice we also went out front and added a sodium ion because this is sodium butanoate. That's the salt that we've created overall. But this is very common or very similar to how we might talk about like NaCl, sodium chloride. Here we have a sodium cation. And the base to which it is associated is the 3-chlorobutanoate anion. There we are. Cation. There it is. Cation. And over here, anion. Nice job, everybody. Cool. Now, things get a little bit more dicey when we deal with cyclic carboxylic acids or carboxylic acids attached to cyclic root chains. It's very tempting to stick with our oic acid suffix nomenclature here. However, I want to point out that's technically not accurate because to stick the suffix oic acid onto the root in the first example, hexan, we got hexanoic acid, implies that the carboxyl group, here our carboxyl group is right here, our carboxyl group is part of the longest carbon backbone. Notice that that's not the case in our current example. Here we have a backbone right here, and sort of attached to but not necessarily integrated into that backbone, we have our carboxyl group itself. Put another way, we need a way to designate that the carboxyl group is, in this case, a freestanding entity. And the way we do that is by simply stating carboxylic acid. That indicates that the carboxylic acid is, in this case, a freestanding entity, and then we can name the rest of the molecule to which it is attached. How many carbons in that ring, gang? What root goes along with number 7? Hept. Yeah, so we call this cycloheptane, just like we would call it if it were just cycloheptane, with a carboxylic acid group stuck on there. Cycloheptane, carboxylic acid. Of course, we've also designated the position of that hydroxyl group as well. But you're going to spot the right name on test day as long as you are following these basic principles. Nice work here, gang. Right on. And then we have this unbelievably long, much more complicated looking molecule, but actually all of the same principles we've learned so far are going to apply to this molecule as well. I see, however, two carboxyl groups. Very simply, how do I modify the suffix to indicate the fact that there are now two carboxyl groups? Yeah, dioic acid. And notice, gang, that the carboxylic acid is always a terminal functional group. It is always going to be found at the end of a carbon chain. So there's no reason to specify via numbers what carbon these particular functional groups are found to. For example, a diol or a dione, we might have to say what numbers they're on. With a carboxylic acid, they're assumed to be at the ends of the chain because that's how carboxylic acids work. So 3-chloro-octandioic acid. Nice work here. Cool. So naming, again, pretty straightforward, much more straightforward than in your organic chemistry classes, because we only have to recognize the right name, or perhaps, not be intimidated even by names on a passage where these names are coming up. Now, physical properties of carboxylic acids. The main thing we want to know about carboxylic acids, in addition to being obviously acids and therefore entering the gateway to acid-base chemistry and making that bridge back to Gen Chem in general, carboxylic acids generally tend to have a higher boiling point than similar molecular weight molecules. Let me ask you guys, why or why might that be? Why would carboxylic acids tend to have a higher boiling point? Yeah, they've got that H bonding. In fact, not only do they have the opportunity to make one H bond, but each carboxylic acid has both H bond donor and H bond acceptor. They can make several H bonds overall. If we compare, for example, acetone, you guys might be familiar with that guy, the universal solvent fingernail polish remover, versus acetic acid. There we have acetic acid. Notice their molecular weights are almost identical. They are extremely similar, except for that the boiling point of acetic acid is about 60 degrees higher than the boiling point of acetone. And Eli's got a great point here. Acetic acid and acetone, these are ones you should recognize on site. You should be able to reproduce their structures given their names. These are ones that the AAMC has traditionally expected students to be aware of and familiar with. Now, the data about boiling points and melting points, you probably are not, I'm going to go ahead and say, you're definitely not going to need to memorize these numbers, but as a relative thing, I want you to recognize the boiling point isn't just higher, it's way, way higher because of those H bonding capacities. Nice work here. Now, boiling point aside, the acidity of carboxylic acids we mentioned as something that is a defining characteristic for them, something that is highly important for carboxylic acids. So let's talk about some of the factors that are going to influence the acidity of carboxylic acids. You see here on screen a great point. The anion, the deprotonated version, the conjugate base, is very stable. Why is that important for acidity? So it makes the acid proton relatively acidic. Why is that important for acidity? And there's a lot of right answers here, so don't be shy. There's a lot of ways of saying the same thing. It's favored, easier to get rid of the H, Bailey. I like it. I see lots of typing too, so go ahead and punch that in there. The deprotonated version is stable. Yeah, stability overall. Keep in mind, gang, this is a weak acid, right? Any organic acid is a weak acid. Any carboxylic acid is a weak acid. What does that mean? Again, if we're making a tie into Gen Chem, let's get our feet dirty here. Let's get all the way into the Gen Chem of this. What does it mean to say it is a weak acid? Lauren, we'll come back to that in just a second, since you brought it up, and I promised we were going to get our feet dirty here. Does not fully dissociate. Yeah, it can be used as a buffer, doesn't fully dissociate. These are actually all interrelated, so not that much more acidic than water itself, Matthew. Yeah, that's a good observation as well. Basically, if this guy doesn't fully dissociate, that means he's going to enter into equilibrium. Enter into equilibrium. So a good way to consider weak acids and weak bases is that a weak acid or a weak base is one that enters into equilibrium. Now, my question is actually one that Lindsay has answered. What does this guy enter into equilibrium with? He enters into equilibrium with his conjugate base, right? We're going to see him in equilibrium with his conjugate base. Now, since it was brought up, if my weak base is also in if my conjugate base, that is also in equilibrium, what does that tell me about that base? It's in equilibrium, so is it strong or weak? Yeah, this is a really key insight, is that weak acids have weak conjugate bases, and the key idea here is that they're both in equilibrium, really with each other. Weak acid enters into equilibrium with a weak base. The key idea here, the reason why stability of the conjugate base is so important, is that we're in equilibrium, right? If I'm going to enter into equilibrium with my conjugate base, that conjugate base had better be relatively stable, and vice versa. What we see is that the acid is pretty stable, the base is pretty stable, and because they're both pretty stable, they have that relative balance, that equilibrium that's so important for weak acids and weak bases, right? The key is carboxylate anions are quite stable. That makes the proton relatively easy to dissociate, to enter into this equilibrium. And the final question for you guys is, why? Why, oh why, would this carboxylate anion, I see it's got a charge, atoms don't like charges, but why would it be so much more stabilized than most situations where we have a negative charge? Resonance. Yeah, exactly. And Bailey's got a great point here. Really what happens is we have three atoms that are sp3 hybridized. The two sp2 hybridized. The two oxygens in carbon are all sp2 hybridized, so that we can pass electron density across this entire structure. You see here, the conjugate base is resonance stabilized. And that's going to overall increase the stability of that molecule. Now, there are other factors that are also going to be influencing the stability. They also have to do with drawing electron density around the molecule, sort of spreading that negative charge around. I always think about it like spreading peanut butter on a bagel, right? Or maybe cream cheese on a bagel, right? You want to get that cream cheese nice and evenly spread around that bagel as possible. Same idea here. The more we can spread that negative charge around this molecule, the better off everyone's going to be. So let's think about how else we can influence the acidity of a carboxylic acid. Think about electron withdrawing groups. Why would these help stabilize the conjugate base and thereby increase the acidity of a carboxylic acid? That's just not a word that you hear outside of the East Coast, man. Schmear. Although it is a cool word. Why would electron withdrawing groups help stabilize the charge? Help stabilize the molecule overall. Yeah, it also helps to spread out that negative charge. It's going to delocalize the negative charge by pulling it towards the electron withdrawing groups. Now, if we take a look at some examples of this, here I've got 3 examples of this. Let me ask you, in context here, why would the molecule in the middle be more acidic than the molecule on the far left? Nice. Yeah, so we see a really important property here, right? The number of electron withdrawing groups is going to influence the acidity of the molecule. How about this? Why would the molecule on the far right be the most acidic out of all of them? I like the way Romancito put it. 2 greater than 1. Yeah, the proximity also is going to play a major role here. So if we rank these in order, you see that more is better than fewer and closer is better than further. But you don't need to memorize all these trends. All you need to remember is that if we can spread negative charge around, then we're going to have a more stable conjugate base, and therefore it's more likely to form, and therefore the acid is more acidic in the first place. And Lauren, yeah, we could call those geminal relative to each other, bound. They're twin chlorides, actually in both cases. Finally, and I see one person who's got this answer already, if the top effect is called a resonance effect, what do we call the bottom effect? It's a different way of spreading charge around. I just want to put a name on it before we leave it behind. This is called the induction effect. Yeah, and then notice, induction and resonance, they have in common that we're spreading charge around the molecule. They are really 2 different sides of the same coin. So we've got a question that we can answer that should directly relate to these principles. I'll go ahead and pull up a poll pod so that you guys can play along at home. If you'll give me just one more second to track that down. Sorry, I thought we had it open already. I'll get that on screen, and I hope you guys are thinking about the answer in the meantime. There we are. Okay, I just cleared out the answers. You all can go ahead and vote in with your results here. Great. Yeah, really just one extra layer of difficulty on this question compared to what we've already talked about. That is, we need to interpret the pKa. It looks like almost all of you have done that correctly. A low PA means high acidity. We see that the inductive effect and resonance are going to be the major factors. Proximity and the number of electron withdrawing groups are the things that influence the inductive effect. And if we draw a quick little diagram of these, it's pretty clear to see that letter C is a direct analog of the example we just saw. It's got more electron withdrawing groups, and they're closer in. That's going to lead us to the lowest pKa overall. Basically a direct application of what we just covered. Nice work, everyone. So let's take a look at our second learning goal of the day. Again, deeply related to biochemistry. The last answer was C, Carissa. Distinguish between different reactions of carboxylic acids. So here we have some specific reagents that are acting on our carboxylic acids. We want to take a look at a few different reaction mechanisms, all of which are very much related to biochemistry. You see this guy, highly reactive. We can think about what makes a carboxylic acid group more or less reactive. Starting with carboxylic acid synthesis. Now, you see on screen, carboxylic acids can be synthesized by oxidation of a primary alcohol or aldehyde. Let me ask you this. What do primary alcohols and aldehydes have in common that allows them to ultimately turn into carboxylic acids? They've each got a bond to oxygen. Yeah, now Lindsay, be careful. Primary alcohols do not have carbonyls. Same thing there, Molly. And then also, aldehydes are not chiral, right? So there's a lot that these don't have in common. They could both be great electrophiles. Yeah, what these have in common is that they are terminal functional groups. They are terminal functional groups that already are to some degree oxidized. And let me focus on that other word here. Carboxylic acids can be synthesized by oxidation. How at a glance could I recognize that converting primary alcohols to carboxylic acids, for example, is a process of Bazinga, more bonds to oxygen. You guys got it, right? So there's a lot of very fundamental chemistry happening here at the baseline of this. Here, again, you see ethanol. Notice some of the ideas you guys mentioned here. This is bonded to oxygen. However, it's an sp3 hybrid carbon versus an aldehyde, which would be sp2. Yeah. Now, again, you guys mentioned that the thing to look for is that we're increasing the number of bonds to oxygen. Let me point out here, the strong oxidizing agent in front of us, potassium permanganate, also has lots of oxygen. So a great way to recognize oxidizing agents is lots of oxygens there as well. We're trying to cut down on the memorization by noticing patterns. Now, a couple of you guys are hinting at this next mechanism. Carboxylic acids can also be synthesized by oxidative cleavage. Notice, again, we're going to be forming bonds to oxygen. When we talk about cleavage, that is to say we're going to break a bond. And in oxidative cleavage, what kind of bond are we breaking? Yeah, we're breaking a double bond. We're going to take an alkene group, a pi bond there, exactly. And the way I like to conceptualize this mechanism is that we're going to go ahead and just split that guy right in half. Just take him and snap him open. Just snap that right in half. And therefore, because we broke it, we have to fix it. We fix it by capping off both ends with oxygen. Your organic chemistry teacher would probably cringe at that analogy because that's not at all the mechanism, but it's a good way to remember this. We're going to break that bond, and now we've got these two broken halves that we fix by capping off with oxygen. We then oxidize this all the rest of the way to a carboxylic acid, and notice again we've made two terminal carboxyl groups. By the way, gang, how can I recognize ozone and peroxide as great oxidizing reagents? Lots of oxygens. Yeah, and also, Cassandra, let me point out, this is called ozonolysis. This is a reaction called ozonolysis as well. This is oxidative ozonolysis. You might also see reductive ozonolysis. Reductive ozonolysis differs from oxidative ozonolysis in that instead of ending up with a fully oxidized carboxylic acid, the end product of reductive ozonolysis is an aldehyde. And the way I remember that is that with oxidative ozonolysis we are fully oxidizing all the way. Reductive ozonolysis is kind of like, it's kind of half-cocked. We only get halfway there. We break the bond, we cap it with oxygen, but we don't then oxidize all the way to a carboxylic acid. So that's a bit of trivia to watch out for on test day. The way you can spot this is we have an oxidizing step, ozone, that's our ozonolysis step, followed by a second oxidizing agent. If I followed up ozone with a reducing reagent, that would be reductive ozonolysis. At any rate, there you are. Cool. Now, when it comes to that's synthesis of carboxylic acids. When we take a look next at reactions of carboxylic acids, we have nucleophilic acyl substitution. Each one of those words means something super important. I'm sure you guys by now are super duper familiar with nucleophiles. Nucleophiles attack electrophiles. What the heck makes this carbonyl carbon here so darn electrophilic? Yeah, exactly. It's got a double bond to oxygen, which is the second most electronegative atom. So the oxygen is going to be pulling electron density away. The induction effect, Aman. That's a great summary from earlier. Yeah, leaving us with a delta positive, as a few of you see. Saharsh and Molly are pointing out there's a delta positive on that carbonyl carbon. It is a great electrophile as well. It's planar, which means it's not as blocked in terms of sterics for attack. We can attack that guy relatively easily. So we have a nucleophile attacking an electrophile. This is a nucleophilic acyl substitution, and I want to point out to you guys here, this functionality right here, overall, everything but the OH group, we call that overall an acyl group. And the reason why that's important, you see here, if I have an acyl group and I add to that a hydroxyl group, that's going to give me a carboxylic acid. Carboxylic acid overall, right? But let's say I swapped out that hydroxyl group, and maybe instead of a hydroxyl group here, I had an amino group. What if instead of this hydroxyl group, I had an amino group? What functional group would we call that? Yeah, that would be an amide, and there's your tie-in to amino acids and proteins, right? Amides are the functional group found in amino acids and proteins. What if instead of an OH group, I had, I don't know, an OR group here? That is, instead of OH, I had oxygen and then another R group. We'd call that an ester. Yeah, so as we start to transition toward the end of this lesson towards carboxylic acid derivatives, it's important to recognize nucleophilic acyl substitution. All of our carboxylic acid derivatives are going to have that acyl group in common. It's the something else that's bound to them. The hydroxyl group, the OR group, the amino group, whatever that thing is, makes the difference between these carboxylic acid derivatives. We're going to come back to that in the end, because what I want to point out to you guys right now is that last word, substitution, implies we're going to knock off this OH group and replace it with the nucleophile, right? So you see we have this intermediate where we pushed electron density. We've changed the hybridization from sp2 up to sp3. Our next step, we're going to push electron density back down and knock off my leaving group so that my nucleophile has indeed substituted out for my electrophile, or for my hydroxyl group, my leaving group. Iman, we'll come back to that in just a second here. But what I want to take away from this, or what I'd like you guys to take away from this, what if instead of generic NU dots, right, this sort of very esoteric notation, what if specifically I used an alcohol as my nucleophile? What would be my end result in this case? Yeah, in this case, the mechanism is going to be slightly modified, but I'm going to end up with an OR group, aka an ester overall. Or you could think, what if I started with an amine, right? An amine is certainly a nucleophile. If I started with an amine, I would end up with what functionality? I'd end up with an amide at the end of the day. Yeah, so again, we learn one mechanism, and there's some slight modifications along the way, but they're all very, very intuitive, and we get a lot of different reactions for free. When we talk about nucleophilic acyl substitution, what we're really talking about is converting one carboxylic acid derivative into another carboxylic acid derivative. And then to Aman's point, is this an SN1 reaction? Well, it's not, gang, and I can tell you that right away, because what super important intermediate do I need for an SN1 reaction? Yeah, we pass through a carbocation intermediate. As well, this is not an SN2 reaction, because what's the hybridization of the carbon in an SN2 reaction? Yeah, sp3, and we pass through that transition state intermediate and end up with an sp3 product. So this is neither SN1 nor SN2. It's a completely different kind of substitution, but I really like that question because we're thinking in terms of the big picture. We're saying, you know what, instead of memorizing a bunch of specific mechanisms, maybe I can group a whole class of reactions into SN1-like reactions. And I can look at a whole different group of mechanisms and say these are SN2-like reactions. And here what we're doing is a third thing. We've got a whole group of other reactions. And we're saying, you know what? These together are nucleophilic acyl substitution. It's almost like we got 3 different drawers that we can open up, and inside each of those drawers there are a ton of specific reactions. But maybe on the MCAT we only need to know the big picture. Cool. Anyway, overall we are removing water, so this is a version of a condensation reaction. Speaking of putting things into drawers, right, the drawer of condensation reactions would contain this type of reaction overall. Now, let's take a look at some of these specific ideas here. Again, I mentioned making amides and esters are both specific types of those reactions. You guys already told me. Amides are formed when an amine attacks the carbonyl of the carboxylic acid. Let's take a look at what this looks like overall. Now, what I want you guys to notice here is that my amide is going to be starting out with 2 protons and ending up with 1 proton, so there's an additional deprotonation step along the way. But it's a very similar mechanism to the one that we just saw. Exactly, Eli. Brand new reaction that's totally different? No. We have a nucleophile that attacks an electrophile, and these steps are followed in the way we just saw. Same thing, esters are formed when a carboxyl is attacked by an alcohol, often catalyzed by an acid. Now, I want to think for a second here. They just kind of tagged this on, often catalyzed by an acid. Well, let me ask you guys this. How good of a nucleophile is an alcohol molecule? And before you answer that, think about a related question. How stable is alcohol in solution? Let's dig a little deeper into this, gang. You guys are saying not at all, they're not very stable. What could an alcohol do? In what way could it break down, let's say? If it's not stable, it's got to break down. In what way could it break down? It could protonate or deprotonate, right? It could dissociate. It could act as an acid. How acidic is alcohol? Yeah, this is so not acidic that we don't even call it an acid, right? That is to say, alcohol can donate a proton to solution. However, it's not very likely to do that. And one way that, if you guys are still having trouble seeing this, I look at alcohol and I see another molecule that looks really similar. Let me draw one on screen that looks really similar here. Instead of that R group, maybe I can swap that out with an H. Instead of an HOR, maybe I've got an HOH. HOH, aka what molecule? Water! Now, if water is stable in solution, it makes sense that the very similar molecule alcohol would be stable in solution. You guys know water, sure, it can spontaneously deprotonate to an extremely small degree, and alcohol can spontaneously deprotonate to a similarly very small degree. Alcohol is actually quite stable in solution. So if alcohol is very stable in solution, what does that tell me about its reactivity as a nucleophile? Good, yeah, we're putting the pieces together, and that's what's really important to me here. This is a very weak nucleophile. It is not a very reactive molecule. So you look at this, you say esters are formed when a carboxyl is attacked by an alcohol, often catalyzed by an acid. They just kind of tacked that on there, but we can do better than that. We can explain why an acid catalyst would really help in this reaction. It's because alcohol itself is not a very strong nucleophile, so we're going to want to protonate this functional group to increase the reactivity of this reaction. And again, my point is there are subtle nuances to these reactions, but they're not trivia. They're all tied together in an interconnected web of knowledge, and you do yourself a huge favor by studying that web of knowledge right alongside the individual facts that make up the strands of that web. Cool. So that's going to be esterification and making amides. There's one more functionality that we haven't yet talked about. That's going to be anhydrides. Great, Rachel. That's really what these sessions are for, is to make those kind of connections. And I'm glad you guys are digging it. Cool. Let's see where we're coming with anhydrides. An anhydride is formed by the condensation of two carboxylic acids. So what we're going to imagine is that I have two carboxylic acids, and they're going to kind of shake hands. I like to think that we're going to smash these guys together and see what happens. Now, this is still a condensation reaction. That means that we're going to drop out a water, and you can kind of watch in blue that water drop out. There it is. We lose the water, and that forms an anhydride. But let me point out, gang, we still have a nucleophile here in green attacking an electrophile here in green, and our leaving group is still going to get pushed off just as it always has. Again, if we learn that nucleophilic acyl substitution mechanism, we get a bunch of different mechanisms, all for the price of one. We end up with this very interesting looking molecule, this anhydride that we've drawn over here on the right. I like to think that the anhydride is so named because it's two carboxylic acids minus water. Anhydride kind of seems to imply that. Nice. Finally, saponification. Let's talk about saponification. The name saponification is a big fancy word to say we have just made soap, right? In what way can the molecule that I've got drawn on screen here act as soap? I'm talking like hand soap, the stuff that you wash grease off, really fancy soap. Yeah, what we see with this is that I have a very long fatty chain and a charged hydrophilic head. So that what we're going to see is that these molecules aggregate together in a micelle. And again, if we're talking about micelles of fatty acids, we're definitely deeply into the realm of biochemistry. We've really got to understand the organic chemistry if we've got a shot at the biochem. So this is definitely high yield stuff for the MCAT. The idea, if you're still not seeing it, is that some sort of molecule like grease or something else that might not wash away would be able to be dissolved inside of the fatty tail part. So if I've got like a fleck of grease, black was a bad choice of color. I've got a fleck of grease dissolved inside of my micelle, and then I can wash my hands with water, and this will just float on away. The water will bind to the water will solubilize the hydrophilic heads and wash that micelle with grease or whatever else is contained inside away. The point is, when we talk about saponification, this is a big $5 word for saying we're going to deprotonate the acid part of a fatty acid. All we've done is pulled off the proton at the end of a fatty acid chain. Nice. Hydrophobic interior, hydrophilic exterior, aka soap. Yeah, good stuff. I like it. Now, let's take a look at another question. You guys can go ahead and vote into this question if we can get our poll pod back up on screen. And Eli, it's not letting me drag that, man. Can you get, oh, never mind, there it goes. TPR, Princeton Review, in here trying to sabotage our rooms, I guess. There we go. You guys can vote in. The poll is all cleared out, and take a stab at this one. Now, what I like about this question, while you guys are kind of considering it, those of you who've already voted in, you might want to think about this as well. Aromatic compounds. I did not think that aromatic compounds are part of the new MCAT. In fact, not only did I not think that, I know that for a fact because they're not listed on the AAMC's website as being important compounds to know about for the new MCAT. And yet, here I see aromatic compounds. And a really great point about this, gang, as you guys are getting closer to your test day, you have learned the boundaries of what is and isn't testable on this test because we built your review notes around the AAMC's recommendations. So put simply, if something's not in your books, it's not required knowledge for the MCAT. When you look at this question, instead of going, oh my God, I didn't study aromatic compounds, what should I do? You should recognize the aromatic element actually has very little to do with the answer to this question. Instead, what this question is all about is the functional group that you do know about, the conversion of a carboxylic acid to a ester. And in fact, we can even take this a step further. We know that in order to turn a carboxylic acid into an ester, what kind of a nucleophile should I use? An alcohol. Yeah. So I look at this and I say, wait a minute, I just need the one that is an alcohol, right? I need to find the answer choice that is an alcohol, and that's going to help me answer this question. Nice. Requires a good nucleophile. And as we're seeing in the poll reflected on screen, there we have it. Nice. Cool. By the way, so Rachel, what was not straightforward about that question, the intimidating element of that question, is that it did involve content that many students wouldn't have studied in advance of the test, right? So instead of freaking out over that, the thing to do is to recognize, actually, this is a much simpler question than it appears on its face value. To answer that question more directly, though, Rachel, consider for every unbelievably hard question on the MCAT, there must be an unbelievably easy question because it's a standardized test with a bell curve at the end of the day. So instead of letting yourself get distracted and saying, no, the MCAT has to be harder than this, remind yourself, actually, we are going to see a fair number of straightforward questions on test day. They just don't stick in your mind the same way that the really hard ones do. Now, in our next learning goal, our last learning goal for the evening, what we're going to be, our second last learning goal for the evening, what we're going to be doing is taking a look at the carboxylic acid derivatives in a little bit closer detail. And again, you see these brought up in biological context all the time. Here we have a ester. Down here we have an anhydride. This is, again, synthesis of a very common compound, aspirin. So you guys are going to see these brought up in biochemistry mechanisms all the time. Amides. We want to think about how we name amides. The way that we name an amide is basically we take the molecule and name it as if it were a carboxylic acid. But then we change the suffix to recognize that it's not a carboxylic acid. For example, what suffix do we give to amides? This one's really easy to remember. That might even trigger your memory. Yeah, the suffix for amide is just amide, or amide. So we switch the name out to be amide. Now we also need to name the thing that's attached to nitrogen. We tack that on out front, and just as we do elsewhere, we give it the N designation to designate that this is an ethyl group bound to nitrogen. Cool, there it is, our final product. We can also have cyclic amides, and when we get a cyclic amide, it takes on a special name. I wonder if anybody knows, what do we call this class of molecules in general? Lactam. Yeah, now we're going to see lactones in just a minute, but I want to point out there's a naming trick built into this. Lactam has an AM because at the end of the day it is an amide. The way these are named is kind of wonky. They're named using Greek letters. Notice that we have the carboxyl carbon, we have an amino group, and we have two additional carbons. We designate those the alpha and the beta carbons, and therefore call this a beta-lactam. What would you guys guess this molecule is called? Think about the third Greek letter. Yeah, this is going to be a gamma-lactam. Bingo! And we can keep going right around the ring here. This last molecule is going to be the most stable because it's got a 6-membered ring. We would call this a delta lactam. Exactly. Nicely done, gang. Take a look at esters. Again, we would name this as if it were a carboxylic acid. Notice they made this a little more complicated, but they named it just as if it were a carboxylic acid. Only we swap out the suffix to indicate that it's not a carboxylic acid. What suffix are we going to give this guy, gang? O8. And then also we need to name the functional group bound to oxygen. Let me ask you guys, what kind of functional group is that? You're close, Cassandra. Tert-butyl would have an extra methyl. Yeah, and Delissa, iso something's a great start. Notice there's 3 carbons, so isopropyl. Yeah, isopropyl. Beautiful. Yeah, this is isopropyl 3-iodo-butanoate. And again, we're only picking the right answer out of a list of 4. Now, if the cyclic amide is a lactam, the cyclic ester is a lactone, and I want you guys to notice they're named in exactly the same way. We call this a beta propanolactone. We call this guy gamma butanolactone. Notice here we are also adding in the addition of the number of carbons. And then down here, delta pentanolactone. Again, notice that in this case, we still have the delta. We still have that lact suffix, that lact root. We're also adding in the total number of carbons. That's what differentiates these from lactams. Great. Finally, anhydrides. These are named in a very straightforward way. Let me ask you guys, what 2 carboxylic acids were sort of monster mashed together to give me this particular anhydride? Yeah, 2 ethanoic acid molecules came together to give me this anhydride, so we call it ethanoic anhydride. There you go, your turn. Name this anhydride. Beautiful. Propanoic anhydride. Now you might ask, Tyler, well, what happens when they're not balanced? And that's a great question. And it has a very simple answer. When it's not a balanced or equal anhydride, a symmetrical anhydride, you just name each of the individual acids that would have gone into this, and then again say anhydride. So this guy is going to be ethanoic, propanoic, anhydride. You just name each of the individuals, and then add the suffix anhydride. Very straightforward. Finally, this cyclic molecule does come up quite a bit, so it's good to know him as well, succinic anhydride. And we have one final cyclic example, similar to the lactams and lactones that we saw. Now there's a question here. We do have one more learning goal that I want to touch on, the relative reactivities of these. So I'd like to assign that question for homework and continue on into this last learning goal. But let's think about the relative reactivities of these various derivatives. What I'd like you guys to think about, the reactivity of the carbonyl is going to be determined by its substituents. So here I have 3 electron withdrawing oxygens. Let me ask you guys, in general, what effect have electron withdrawing groups had on reactivity so far? Yeah, we saw that more electron withdrawing groups meant more reactivity, and that's the case here. What we're going to see is that this molecule, anhydrides, are generally quite reactive, and you can see there's some resonance stabilization in addition to the inductivity effects, and that's going to be helping us with the reactivity. That's to say, we can stabilize the positive charge on these molecules, making them more electrophilic. Great. But let's contrast that with, for example, an ester. Now, why might the ester be somewhat less reactive? Yeah, there's simply less electron withdrawing oxygens. This guy's only got 2 electron withdrawing oxygens. Nice, Romancito. 3 is greater than 2, simple arithmetic. And then finally, our amide, you could consider this guy as the least reactive because it only has 1 oxygen and in fact now has an electron donating amino group. Good thing too, because remember, this is the bond that holds together proteins, so we would expect it to be quite stable overall. If we're looking at the reactivity of these derivatives, what we see is that my amide group is the least reactive, the most stable, and my anhydride is the most reactive over there on the far left-hand side. As well, we would expect steric effects to play the same role that steric effects usually play. Here we see the molecule on the left, less steric hindrance, easier to attack. The molecule in the middle, more steric hindrance, less reactive. So what I remember about this, gang, is that steric effects do the exact same thing here as they always do. And we see more hindrance, less reactive overall. Now, let me ask you guys a good question here. At any time, what is the best way to solidify the knowledge that you have gained in one of these lessons? Go out and practice, practice, practice. Therefore, we've assigned you guys a practice passage that ties into these ideas. It's a really great passage. You guys can hit the Q bank for more practice as well. And of course, you're going to see this showing up on your biochemistry sessions as well. We have answers and explanations in the recap document on the next screen. I'm going to be back in 5 minutes to do some full-length 4 review. So if you haven't yet taken full-length 4, you're probably going to want to sign out at this point. I want to say in the meantime, thank you guys so much for the work you did tonight with me, with Eli. Maybe I'll see you back here in 5 minutes, but if not, I will certainly see you in a future channel session. Thanks, everybody, and we'll see you back here real soon.